Okay. So welcome to the midterm exam. My name is Matt, one of your TAs. Many of you probably know me. I'm going to be walking you through one of the midterm exams that he posted on Canvas. Has everybody had a chance to look at that or see it? No. Okay. Does everybody know where you can find it?
Yes. I'm assuming somewhere on the Canvas page.
Okay, yes, it's under modules, under one of the weeks. I forget exactly which one. But it has both this midterm exam from spring of 2019, and it also has the midterm exam from spring of 2018. If you want my honest opinion, it would be very worth your time to go through and look at both of those. If you do, you might notice some similarities in that they almost look like the exact same exam.
17 is up to most recently.
That's no real coincidence. I wouldn't be very shocked if your coming exam looks very similar, or at least posed really similar looking questions to the ones that these exams have. In the same order, more likely than not.
We'd love to hear that.
All right, so before we begin, the screen's not really going to capture this, but I would also want to go over a couple of the things that, let's see, you are allowed one sheet of notes. So I want to go over, what do you think are some of the things that you want to put on that sheet of notes?
Dijkstra's and BFS and DFS.
Okay, you're hinting at something. I'm hearing a lot of algorithms being put out. I'm going to write this up real big. So what class is this?
Algorithms.
This class is called Algorithms. You're going to want to write all of the algorithms, at least all of the names of all of the algorithms. And what are you going to want along with each of these algorithms?
Complexity.
Complexity, yep. So you're going to want complexity.
Probably some pseudocode.
Pseudocode, or at least a general idea of what it is. I wanted to write gist up there, but I don't know how to spell it. So one more question on graph algorithms, right? Do you think all of the questions are going to be about adjacency lists?
No.
No. You're going to want to make sure on your complexity that you include not only the adjacency list complexity, but also the adjacency matrix. Both of those are going to be important. I remember when I took this class, I can't remember, I think it was fall of 2019. When I took this class, one of the most important things for me was just having that list of every algorithm that we went over, and right next to it just its complexity. And if it was a graph algorithm, I would have two complexities next to it, one for the adjacency list and one for the matrix. Most of the time, and y'all are really familiar with this, when you're giving a sheet of notes for an exam, you look at it very rarely during the exam, but having that list of algorithms, I did actually look at it during my exams, so I can vouch it does help. Does anybody have other suggestions of things that you might want to include on your one sheet of notes? Vocab?
That's something that always gets me. Tests is just the definitions of words. If that's if there's any weird words that have been introduced in the class.
That might actually
more
be
relevant for OS, but
that'll be relevant for here, knowing what a DAG is.
Yeah.
Right?
I always
Things like
forget
that.
what the specific term for that thing is.
Mm-hmm. That would be good. Is there a suggestion back there?
So is it, I forgot what it was, it's like the table with what dominates what?
With the what?
The dominancy table or whatever that was?
Oh, the dominance table. That would be excellent to include. Knowing whether polynomial is better than logs, or which combination of them is bigger than the others. That would actually be really good to include. Is there another suggestion?
The doubling behaviors.
Doubling behavior. Ooh, that's actually excellent. And we're going to see a perfect example of that real soon. So yes, you're probably going to want to include the doubling behaviors as well. Okay, and then one more, and then we'll start going through things.
The Sega Master Theorem?
A master theorem.
Didn't he say that the
It's on the master.
Ah, there we go. So the master theorem is in fact included on the test. Oh, look at that, it makes a square. This is my wife's Surface. I don't use it very often, but it does some pretty snazzy things sometimes. I have one I have one advantage using this thing than y'all do. I guess I don't have the hotkeys on me, but I could just like take a screenshot of that and move it around with me wherever I go. But when you get to the exam, like it may help to have your own master theorem just written out, if only for the sake of you understanding it before you get to the exam. But yes, it will be provided if you don't include it. So before we start going through these, I was planning on just going through them sequentially. But does anybody have any questions that they would like to get to right away, right? Does anybody have any like burning issues that they really don't understand? Or can we just start going through them one by one? I don't see any hands. All right, then. I'm going to take that as an excuse to, oh man, this looks real familiar. All right, question 1. The best cases, and I have taken the liberty of underlining and drawing an arrow to best cases, of 4 algorithms are carefully timed on arrays with n elements, dense graphs with n vertices, binary heaps of size n, and balanced binary search trees with n nodes. A different computer is used to time each implementation, and then it provides you a table of all of their behaviors. So what is something you notice right away about the very first column of this table, the n column? It's doubling, right? It's using best practices from this class. So that's something you're going, that is not a 2.
Sometimes the auto finishing is not.
So that's something you're going to want to pay attention to. Like you can't just draw a scatter plot or anything like that and like see, oh, this looks like a line. This is using doubling behavior for n, meaning that it's going to be really important that you remember what each of the doubling behaviors is associated with. So when I took this class, I took it from a different instructor. This was still the very first question on the test. If you look at the 2018 midterm, this is still the very first question on the test. It uses different algorithms and different examples. So you're going to want to know each of their complexities, but you're also going to want to know how to analyze the doubling behavior. But whenever I take one of these, the first thing I do is, because I'm not always 100% on all of the algorithms, like their exact complexities, but I can know the basic ones, the easy ones, right? What do you think would be the easiest case? Like W, X, Y, Z, which would be the easiest to start with?
Binary heap is Y.
Oh, what on earth just happened? I clicked the pen and it's loading something.
Oops.
It looks like it.
Dropbox organized. Bug about.
There we go. Do not click the pen. I've learned something. So we're looking at algorithm Y, and it looks constant, right? It's taking the same time all the time. Which of these algorithms would take constant time every time in the best case? Just inserting into a binary heap.
Putting it on the bottom and then don't move it.
Exactly. Did everybody hear that? So in a binary heap, right, the way it's organized, I'm going to draw a real small one. Oh man, circles are great.
Except some of them are not circles and it's
There we go. Okay, y'all understand what's going on there. So in the binary heap, each of these nodes has numbers in it, right? And say we wanted to insert the number 3. Well, the first thing we do is we insert it way at the bottom, a little 3. And let's say this number up here was a 2, right? And so the property of the binary heap is that at every node, each of its child nodes is greater than it, right? If this is a min heap. So in the case when we insert 3, it already still follows this property, so we don't actually have to do anything else. So that's constant. So we can know that an insert into the binary heap in the best case will be constant time. So that one's good. How about algorithm W? So it looks like it's got 50 to 120, which is a difference of 70. 120 to 190, which is another difference of 70. Right? So it looks like it's going up by the same amount every time. So when we look at doubling behavior, what does that tell us about its behavior?
Log n?
It's log n. Yes. Exactly. So that's important to remember, is if it goes up by a constant amount during the doubling behavior, that means it's log n. Now, which of these algorithms looks like it would be log n? Binary search tree. Yes, because I mean everything BST is log, right? Sweet. Then we have, looks like algorithm X, we've got 9, then 18, which is double, and then 36, which is double again, right? So if n is doubling, and our runtime is also doubling, what does that mean for the complexity of the algorithm? It's linear. Now, there's two ways you can approach this. Either you can have the complexity of quick select memorized, which not everyone will, unless you have it on your note sheet. Or you can kind of just do series of elimination. I know Bellman-Ford is not linear, right? Right? I'm pretty sure it's some exponent. I don't know exactly what it is, but I do know it's not linear. So I'm going to go ahead and say quick select is probably X, and Bellman-Ford would be Z, right? So you can also like look at the complexities yourself. Analyze algorithm Z. It's multiplying by 4 every time, meaning it's actually quadratic in the best case. But I like to do series of elimination for these, and more than likely when you do it, there will be whatever the last one is should be fairly easy to identify. Does anybody have any other questions on number 1 or questions that look like number 1? Yes.
Remind me, what is a quick select?
What is a quick select? Okay, that's a good question actually. So a quick select algorithm is given an unsorted array, right? Say you want to find the ith biggest element in that array. So if the array was in sorted order, you would want to find the ith element. And so what quick select does is it does the partition just like quicksort does, but then it only checks one of those, like, it only checks 1/2 of the array in order to look for the ith biggest element. So it's basically like half a quicksort, essentially. And you can use the master theorem actually to see that it has a linear runtime. Quick select is described in one of the lectures. I don't remember the exact lecture number, but you can find the slides for it on Canvas. Anything else, or are we free to move on? I think we'll move on then. Oh, here's another fun one. All right, number 2, solve each equation below for x, which must be, I'm going to underline this one too, x must be a non-negative integer less than the modulus. So x cannot be a fraction, and x cannot be negative. It's really important for some of these, and it'll be more important for, I think in your next lecture you're going to go over modular inverses. There's a question like that on the homework already, if some of you have seen it. So we can probably go through these ones pretty quick. What is the answer to the first one? 6 plus 4 mod 7. It would just be 3, right? 10 mod 7, the remainder is 3. 3 times 5 is equivalent to x mod 9. 6. Because once again, we have 15 mod 9 would just be 6 as the remainder. Is there a question back there?
Could you turn the lights off?
Lights. Yes, I can try. Let's turn on. Let's turn off. Oh, that's too many. Is that good enough? Can people see?
Yeah, that's good.
Can people stay awake?
Yeah.
All right. So this one is an interesting one. I've rewritten the question here to the side just for reinforcement. But 3 times x is equivalent to 1 mod 10. 7. So let's test that out real quick. 3 times 7 equals 21, which when we mod 10 is equivalent to 1 mod 10. So then our answer here would be 7. So I've written to the side, this is the same thing, this is asking the same thing as what is 3 to the negative 1 mod 10. what is the modular inverse of 3 mod 10? Like, these are asking the exact same thing, is what times 3 is equivalent to 1 with that modulus? I think you'll go over it more during next lecture, but if you are doing the homework and you come across a question like that, this is what it means. And then the very last one, oh, I forgot about that one. Okay, the very, very last one is 2 to the loss of 4s into 6 is equivalent to x mod 15. Oh, man. Does anybody know where we can begin on this one?
We separate the exponent somehow to make it 16 to the very, very, very large exponent. It's x mod 15. And then
That would be
16
excellent.
mod 15 is 1.
So 16 is 2 to the what?
4.
2 to the 4. All right, let's do a quick check. Is this big number divisible by 4?
I can't read that big number, so I don't know.
It's a lot of 4s into 6 at the end.
Oh, that's fair.
If it was all 4s, it would be divisible by 4. That 6 at the end ruins it, doesn't it? It's not, so we can't get it to a 16, meaning we can't get it to be equivalent to 1, which is what I wanted, but can't always have the easy stuff. So, but you're on the right track. So what could we like reduce it to? Is there?
We can multiply it after that by 2 to the power 2.
Mm-hmm.
I mean, we can write it like 2 to the power 4, and after that we multiply this one to 2 to the power 2. It becomes like 4.
You know, that probably works. That's not the way I did it, but I bet that would work. So the way I did it is, I know this big number is not divisible by 4, but I know it is divisible by 2, right? And so I don't have to write all of that out, but that reduces down to 2 squared to the 2, I'm just going to write some dots. And then there's a 3 at the end, right? We don't need to know exactly what it is, but all we need to know is that this big exponent is an odd number. All right, so once again, we can just rewrite that as 4 to the big 2, 3. So 4 to an odd power mod 15. So we kind of already went over this, but if this were an even power here, what would 4 to an even power be mod 15?
1.
It would just be 1, right? So what if we took this and we split it up a little bit? We took 4 times 4 to 2, and then this time it ends in a 2, right? Can everybody see that these two things are the same? All right. So using our mod rules, we can replace one of these terms, mod 15, by whatever it's equivalent to. So what would 4 to the big even number be equivalent to mod 15?
1.
It would just be 1, right? Because we can change it to a 16 to something. So then this would be equivalent to 4. That is not at all what I did. Okay. This would be equivalent to 4 times 1 mod 15. And if you look at the rules above, 4 is definitely not negative, and it's definitely less than 15. So that is our answer, is 4. I can guarantee you're going to see a question like that on the midterm. Some big modulus that looks unfair. And the answer is always going to be some variation of like figure out how to split the big exponent and then use the mod rules that we already know how to work with, right? And the answer is usually going to be 1 or 1 minus the modulus or the thing that you originally started with. This one's actually a little bit unique in that it comes out to 4 instead of 2, 1, or 14. Question?
So what's this? I mean, there's clearly some sort of rule that I'm not remembering where you can pull the 2 out of the exponent and it divides it by 2. Can you just walk me through that? Like,
Yeah, that's an exponent rule.
Okay.
In general, is if you have if you have x to the ij, that is equal to
actually,
x to the I to the j. Those are the same thing.
are there any other
Yes.
It's sort of problem.
I'm going to say there are other exponent rules you should remember. I don't know if I can like spout all of them out. Thank you, Windows. One important thing, this isn't going to be important for the midterm probably, but it will be important for your math careers later. This is not equal to x to the I to the j, right? These two things are different. I have seen people do that. I've been guilty of it too, but just remember these two things are not the same. But this is. Okay. Before we move on, actually, I do think it's also important to know, so we were able to do this step right here. We're drawing all over the next question. We were able to do that step right there because we knew that big number was divisible by 2. It's real easy to see if something is divisible by 2, right? Just have to check if the last number is even. Is it also easy to check if something is divisible by 5? Yes, right? If you see a 5 or a 0 at the end, that means it's divisible by 5. Does anybody know how you check if something is divisible by 3?
Add it up, add the digits up, and then if the sum is divisible by 3, then it's divisible by 3.
Exactly. I'm going to repeat that a bit louder.
Yeah, go right ahead.
So if you have some gigantic number and you want to decide if it's divisible by 3, the trick is to add all of the digits up for that number, and then whatever that sum is, if that sum is divisible by 3, then the whole number was also divisible by 3. The same rule applies to 9 as well. If you have a big number and you want to check if it's divisible by 9, add all of the digits, and if that sum is divisible by 9, then the whole number was also divisible by 9. As far as I'm aware, there are only rules for checking if something is divisible by 2, 3, 5, or 9, and I guess 10. But all of those might be important to know if you want to try and factor and reduce a big exponent down to something littler. I just said littler. Okay.
Let's take a look at a rule for 6.
If it's divisible by 3 and 2.
Yeah.
Okay, yeah. So you can check if something is divisible by 6 by adding up all the digits and checking if it's divisible by 3, and then checking if it's even. So that works too, I suppose.
Like, this is not relevant to this, but
Yeah, it might be. I haven't seen the midterm.
that's,
There could be a 6 in there.
I don't know if I believe you, but
All right. Okay. So now that we're done with 2, we spent a little bit of time on that, but modular arithmetic is new. I want to make sure it's fresh in everybody's mind when the midterm comes around. But now that we're done with that, we can move on to question 3. So answer the following questions about directed graphs with V vertices and E edges. So real important to know, these are directed. So question A, is it possible to topologically sort any such directed graph?
no,
No.
I got that wrong.
Well, hang on. Can't you, like, what's the algorithm for topologically sorting? Isn't it just a depth first search from somewhere where you sort by the post time? Can't you do that on any directed graph?
It has to be acyclical, otherwise you're going to end up in a circle.
Right. So you could still do that algorithm. You could still sort it by the post times, but the resulting list is not topologically sorted. Because I wrote here, what property does toposort have? As you're going through the list that you have sorted, no node should have a path leading to anything earlier in the list. So if you have a cycle in your graph, there's no way you could ever sort such that there would be no node with a path to something earlier in the list. The cycle would always break that. So you can only topologically sort a DAG. And our question B is a little bit related to that. If such a graph is a DAG, how many strongly connected components does it have?
1?
Ooh, I heard 0, I heard 1, and I heard the right answer.
My answer is obviously dumb.
No, it's just wrong. So I'm going to walk you through about here. So in a non-directed acyclic graph, so rather just a directed graph, a connected component is comprised of a set of vertices that can all reach each other, right? So, I mean, for shorthand, we can say there's a cycle. There exists some cycle that all of those vertices can reach each other. So, in a DAG, I just draw a quick DAG right here. There's my DAG. That is not, okay. Okay, this is my DAG right here. There are no cycles, right? It's directed and it's acyclic. But if I start at this node, what are all of the nodes like? Can this node reach itself? It can, right? It's already there, right? It has a path length of 0, but it can reach itself, right? So if we were to separate it into its strongly connected components, right? This would just be its own strongly connected component, right? If you want to be a little bit more concrete and we were actually to run the algorithm of strongly connected components, we would actually be starting from the sync node, right? We would call explore on the sync node and check all of the nodes that it can reach. Well, it can only reach itself, so we remove itself from our list of nodes that we're going through and make it its own strongly connected component. And then we would move on to the next node in our reverse topological sort. And we'd come across this one. And then we try to call explore on that. But since this node has already been removed, the only thing this one can reach is itself. And likewise, when we get to the source, we realize the same thing. The source can only reach itself. So, in a directed acyclic graph, and if you want to know how many strongly connected components there are, the answer is going to be V, the number of vertices that you have. This is even true of graphs that aren't even connected. There would be 4 strongly connected components in a graph that looked like that. Is everybody okay on that? I just wanted to make sure we all understood, because when I was reviewing for this, I actually got both these questions wrong.
So if it's not directed, then any nodes that are connected are strongly connected components, or you can't have strongly connected components.
Ooh, that's a really, really good point to make. Right? In an undirected graph, right? So if these aren't directed, can this node reach itself first and foremost? Yes, it can. Can it reach this one? Yes, it can. Can they both reach each other? Then yes, this is a strongly connected component. And anything connected to this little segment would also be strongly connected. That's actually a question on one of these midterm exams. I can't remember if it's this one or the next one. It's probably the next one.
So if this said undirected instead of DAG, the answer would be 1.
No.
It depends on if they're all connected.
It depends on if they're all connected.
Okay, fair.
Right. Like in this example, there are 2 strongly connected components in this undirected graph. So it would give you that information, right? It always gives you enough information to solve it. Question?
So wouldn't it be at most E in this case? If
At
it was
mo-
undirected?
If it was undirected,
Cap would be,
at most E.
that makes sense.
No, because you can have 0 edges and 8 nodes, and then there would be 8 strongly connected components. So at most V would work. Okay. Everybody fine on that? We're free to move on? Sorry, I'm spending a lot of time on these. Okay, question 4. This is another one of those questions that I've seen on every single midterm from this class. So you're probably going to see something like it. So consider the following method. I'm not going to read the code. You can read and see what it does for itself. Return total, though, at the very end. So like you can see, we're accumulating this variable total that starts from 0, right? And the question is asking, what does f of 2 times k return, assuming that k is greater than 0? Give your answer in terms of k. Give a simplified expression that does not include a summation, or one of these symbols. So if anybody has looked at the midterm on Canvas yet, which it's not something a lot of people have, you should still do that. You'll notice I've actually gone and drawn a big angle right here. This is actually a 2-axis graph that I have drawn because I like to solve these questions in a particular way. So I have an axis for I and an axis for j. And what's going to happen is every time we run through this innermost part of the loop, I'm going to draw a little dot, right? And then at the end, once I have like drawn all of the dots, like for every value of I and j, I just want to add all of those dots together, and then that will give me the total answer in terms of k. So it'll be a little bit easier when we run through it. But to begin with, we're asking specifically about f of 2 times k, right? Meaning our n here is going to be 2k. So we're going from I equals 2. So I'm going to see if I can zoom in on this and not touch anything else on the surface. Nope, and there it goes. We're starting from I equals 2, and we're going up to I equals 2k. So I'll go ahead and draw 4, 6, because we're incrementing by 2 each time as well. And j is also incrementing by 2. Like, these are all details that you're going to have to look out for as you approach a problem like this. So when I equals 2 and j starts from 0, how many, like how big is j going to get up to? Well, I guess it says right here, so long as j is less than I, right? So if j starts from 0 and j is incrementing by 2 every time, it's only going to run this inner part of the loop only once, right? Oh, come on. There we go. So j starts as 2. What is going on? There we go. I'm plugged in, right? 2, 4, 6, 8, 10, and it's going to keep going up like that. So on the first iteration of I, we're only going to have just one dot, right? Because j starts at 0, and then when we add 2 to j is equal to I, and it's going to fall out of the loop. So on the next time through, I is going to be 4. So j starts at 0, and j increments by 2. We're going to have 2 dots, right? We're going to go through the center of the loop 2 times, right? And so when I equals 6, j is going to repeat 3 times, right? For 0, 2, and 4. So we'll see this. So we'll have 3 dots. And so I'm sure you can see the pattern already, but I'm going to skip to the end then. When I equals 2k, how many times are we going to go through the center loop? How many times are we going to call total plus plus? K times, right? So I'll start drawing k dots, and then dot, 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 boom. There you go, k dots. All right, so that's actually nice and straightforward. So how can we make a sum out of this, right? Because clearly we start from 1 and we go all the way up to k. So what would our sum be?
1 plus 2 plus 3 plus
1 plus 2 plus 3 plus 4, right? So if we were to make a summation out of that, it'd be the summation from I equals 1 to k of I, right? And does anybody know how to very quickly solve what the summation would be?
It's like I times I plus 1 over 2 or something?
Not I. K.
K plus 1 divided by 2.
I'm going to put that on my sheet.
Oh, that would be excellent. You are going to need, that's an equal sign. You're going to need all sorts of summations probably. You're going to want to understand geometric series, right? The a times 1 minus r to the k over 1 minus r. You're going to want to know arithmetic series, the arithmetic series are pretty easy like this. You're going to want to understand those if you don't already, because on a question like this, they will come up. So here we could simply say k times k plus 1 over 2, if you wanted to do it in line. This qualifies as a simplified expression because it does not contain a summation. But if you wanted to, it's also equivalent to say that, that's too many lines. It's k squared over 2 plus k over 2. Those are the same thing, right? You can reduce it both ways. But I would accept either of those answers. Does anybody have any other questions on that one?
So 1/2 times k squared plus k still count as?
1/2 times k squared plus k, and so the k squared plus k is in parentheses, right? Okay, yes, that would still count. I mean, it's the same thing. Like any algebraic manipulation you do, it's still okay, so long as it doesn't make it look even more complicated than it is. Okay, question 5. How are we doing on time? Doing pretty well. Okay, for each pair of functions below, write theta g if f is theta of g. Otherwise, write big O of g if f is big O of g, or big omega of g if f is big omega of g. And so I have went ahead and written a little note. What do these mean? Right? When we say f is big O of g, what does that mean?
F is dominated by G.
F is dominated by G. What's another way of saying that?
G is bigger than F.
No.
No.
Sorry. I'm quick to correct people on that one. G acts as an upper bound on F. F is bounded from above by G. That does not mean that G is strictly bigger than F, although they seem related. But G is an upper bound on F. Likewise, if F is big omega of G, what does that mean?
F is an upper bound of G.
Yeah, F would be an upper bound of G, or G is a lower bound on F, right? And neither of these are strict. And so if something is big O and big omega, what does that mean?
It's theta.
It means it's theta. Excellent. So we have an understanding of what each of those means, so we can probably start moving through these functions and evaluating them. Unless anyone has any other questions about big O and big omega, because those are also important concepts for this midterm. Okay. So n cubed and n squared, what is their relation?
Omega?
F is big omega, that is a huge omega of G.
Big.
Right? Because G bounds F from below, but not from above, right? That one's easy to see. How about log n and n to the 0.000000001?
Big O.
Why do you say that?
Because polynomial is dominant over log.
But the polynomial is so small. Look at it. It's tiny.
Eventually it'll be bigger though.
Eventually.
One day.
I've done the math on these ones. I love doing the math to see where they cross. The number where n to the 0.0001 like crosses in front of log of n is like 700 digits long. But it exists, right? If you compare them together, like if you do L'Hopital's theorem against each other, like and let them fight, the polynomial will win. That's what I say every time I do dominant stuff. Is like, let them fight. Okay, 5 to the n and 5 to the 2n. This is where exponent rules come in handy. I'm not hearing anything.
Theta? Because it should be 5 to the n and 25 to the n, right?
So, oh, is there an answer back there? Why is it theta?
Because, like, let's say you split it, if you take out, like, the 2 and the constant, it'll just be 5 to the n anyways, so they're just, like, close to each other. Kind of, like, that's the whole gist of it.
This is what the question is trying to trick you into thinking. Right? So when you think of big O, big omega, and theta and all that, you think just drop the leading constants, right? And you can do that for stuff in front of polynomials. But if your constant is in the exponent, right, we can turn this into 5 to the n versus 5 squared to the n, right? Which is, again, the same thing as 5 to the n versus 25 to the n.
Which is always better.
And it's not just that it's always bigger, it is an upper bound over 5 to the n. 5 to the n cannot catch 25 to the n any more than n squared could catch n to the third. Right? That's something important, is when you're looking at exponents, the bases matter. The bases are everything. What was that?
The constants only matter when they're otherwise the same. Like they're both exponential growths here, so that's when we give them about the constants. Ditto with logs, I believe. If they're both log n's, then that's when the constants actually matter. But until then,
I think actually logs of different bases only differ by a constant. I could be wrong about that though. I'm pretty sure they do though. I'm not going to prove that one though, because that's not super necessary. But here, once again, we have f is big O of g. F is bounded from above by g. All right, and then here's the fun one. Log of n to the n versus log of n factorial. Did he walk through the proof of this?
I don't remember. That was a while.
Did he not? If he didn't walk through the proof of this, then you would not be expected to know this on the test. But the fun part about both of these is they can both reduce to the same thing. So log of n to the n, using log rules, we can see it's just n log n, right? And log of n factorial, if you do some fancy proof that I don't actually remember all of, you can see it's actually the same thing. It is also n log n. So these are actually the same. Again, though, if you didn't actually walk through that in lecture, I don't think you would be expected to know that on the exam.
he did.
He did go through it on lecture.
Yeah.
Oh, it's open game then. You better study that. My bad.
I was starting.
So then I'm going to draw a box, and my surface is going to autocomplete it for me.
Maybe.
There we go. Remember that. Any other questions on the dominance hierarchy for functions?
So if you like on that bottom one put some constants in there, is it going to be the same?
Constants where?
I guess both, either in the exponent or just like in front of the n.
So let's see. If you put a constant in front of this exponent, right, n to the 3n, well, that would just turn into 3 times n log n, which is just a leading constant that you can drop. If you had the 3 in front of the log, well, I mean, that's the same thing. You can just drop that. If you had the 3 in the base, logs of different bases only differ by a constant factor, so even that one wouldn't matter. And I can't figure out, oh, what might matter is this one. I don't know if the proof holds for 3n factorial, although I can't see why it wouldn't. So I'm of the opinion that a constant anywhere in here wouldn't matter. If anybody has a different opinion, feel free to shoot me with that one. But I'm pretty sure constants in these cases don't matter at all. Okay, actually, that's not true. If you did have a 3 out here around the whole log, that one would matter. Sorry, I just thought of that one. Okay. I've erased my box.
On in a box.
It's gonna escape now. Okay, number 6. Use master theorem to derive a tight upper bound on the following 3 occurrences. Again, using the power of the surface, I have relocated the master theorem in between these 2 pages for our convenient look. But in the real exam, you could just look to the front page and you would see it there. I don't think these ones are terribly difficult, except for maybe the second one, but we can just go through them. So for the first one, what is A? 3. What is b? 3. What is logba? And by logba, I mean log base b of a.
1.
All right. And what is d?
1.
All right. Are these equal?
Yeah.
Okay, then it looks like that means
N log n.
n to the 1 log n, according to Master's theorem. And I don't know how the proof of that works, but Master's theorem tells me to do that, so I'm going to do that. Hasn't led me astray yet. Second one, what is A?
8.
What is B?
2.
2. What is logba?
3.
3, right? Because 2 to the 3rd equals 8. So we can just substitute it there and we would get 3. All right, and what is D?
2.
More than 2, less than 3.
More than 2, less than 3. I like that. So we don't fully know what D would be, but we do know it's less than logba. Sorry, I like to pronounce formulas just out loud.
It works.
Stop me if I say something really weird, but no. So we know D, whatever it is, it's greater than 2, but it's certainly less than 3, right? Because if we were to look at n squared log n, well, n squared log n is certainly less than, or dominated rather. I don't know how to draw a dominated symbol, so I'll just say it's O. It's certainly bounded from above by n to the 2.00001, right? And 2.00001 is certainly bounded from above by 3. So then the answer for this one would be n to the logba, which in this case is 3. So n to the 3. And try not to include the log in your exponent if you can avoid it. Like, instead of saying log base 2 of 8, try to replace that with 3. If you are given something like log base 5 of 7, then, I mean, you wouldn't be expected to simplify it. Unless you happen to have that one memorized, in which case I'd be very impressed. But you do not get a calculator on this exam, so I kind of doubt it. All right, for the last one, what is A? A is 1, right? It's an invisible 1, but it's there. What is B? 2. What is log base B of A? Right, because log base anything of 1 is 0. And then what is D? D is 1, n to the first, right? So D is greater than log base B of A. 1 is greater than 0. So our final answer is just going to be n to the D, or in this case, n to the 1, or just n. Question?
Do we need to be writing big O of n, big O of n cubed? Or
It says bound, so yes, you should be writing big O's. Meaning I should be writing big O's.
Jeez.
Amateur.
Failed us. You failed the test.
What are they even paying
No
me for?
longer be a TA.
Thanks for catching that. That's really important. Anybody have any other questions about Master Theorem, how to use it? I don't see any. Okay. Wait.
Given an actual algorithm like a pseudocode, how would you determine D?
How would you determine D?
Yeah.
So let's see if there's a question like that here. Oh man. So I'm going to skip 7 and we're going to go to 8. And let's try and figure this out. So consider this function g, which operates on an array of ints. And spoiler alert, g is recursive. It calls itself. And it calls itself twice. And so what we are trying to do is we are trying to find the recurrence relation of it. And it's also going to ask for the bound, right? Yes. So in this case, let's look at what g does. First thing it does is it creates b which is a new array containing the first third elements of A. That kind of gives me a hint at what B is. And C is a new array containing the last third elements of A. So it doesn't actually do anything with the middle third. That's important to realize. I missed that the first time I was doing this problem. So it uses the first third and the last third, and then it returns the max of G of B and G of C. So there's our recursive call. And it looks like there are two of them. So real quick then, in this case, what would A be? 2, because there are two recursive calls. What is B? 3, because we are reducing our problem by a factor of 3. And now the question is, what is D, right? So in order to find D, this is getting towards your question, we need to look at the rest of the function and think about the complexity of each of the individual components. So, for instance, if we just look at the if statement, an if statement is, well, it's a dot length, which is a constant check if the array has its own length stored. So this would be constant, or even if at worst it doesn't have its array length stored, it would be O of n. All right, B is a new array containing the first third of the elements of A. The thing that tips me off here is it's a new array, right? B is not just a pointer, it's actually a full copy of the array. Which, even though it's only the first third, that's n over 3, that's still linear, right? So both of these are also O of n. And then the last part, the max between the two arrays, or actually no, this isn't a max between the two arrays. This is only a max between two values. So what would the complexity of that be? Constant, right? So that's O of 1. So let's look through all of the stuff that we've done so far. We have a constant, a linear, and another constant. So what would be the complexity of everything that isn't the recursive calls? Linear, right? Because it's whatever the biggest complexity of the component parts would be. So in this case, D would be 1. So now let's try and figure out our bounds. We have log base 3 of 2. I don't know that one.
It's less than 1 though?
Yeah, because what would be 1?
Log base 3 of 3.
Log base 3 of 3. Okay, so this is less than log base 3 of 3. Which is equal to 1, so it's less than 1. And hang on, D is equal to 1. So if only the master theorem were... Oh my goodness, it's here too. All right, so looking at this, it looks like log base B of A is less than D. So our answer is just going to be O of n to the D, which is 1 in this case. So it's going to be a linear 1.
It's following us after you poked a hole in the box.
It's everywhere. Did that answer your question?
It did, thank you.
Excellent. Did everybody follow that? Okay, excellent. So don't worry, we are going to get back to question 7. It's one of the infamous true-falses. These ones are horrible because 7 is worth 8 points, meaning each of these true-falses is worth 2 points. And can you get partial credit on any of these?
No.
Nah. Not even close.
It's either true or false.
You're
either right or you're wrong.
We can't see your work for these, so I hate these questions, but they exist. And so you've got to make sure you're prepared to know your stuff about the things that we've learned in this class. So below are statements about a call to a DFS algorithm, depth first search DFS, on graph G. Classify each as true or false. A, I haven't read these in a while. If G is undirected, DFS will always call explore once per connected component.
True?
Why do you say true?
Because it's only going to explore the things that it hasn't visited.
Right, and so in a connected component, do we all understand what a connected component is? It's not quite a strongly connected component, but this is an undirected graph, so everything that's connected to each other makes up a connected component. Right, so if you call explore on this connected component, well, it can reach everything that it's connected to, everything that's in that same partition as it. Partition's not the right word. It might be, but. So in this case, I can't think of any way it would be false. Can anybody else come up with a counterexample? I saw a hand up over here.
I was about the previous problem. I don't want to.
Oh, well, I mean, it's still important to know. Master theorem's good stuff.
So in the previous problems, I guess on number 8.
Oh, number 8? Okay. Yeah.
Wouldn't the tightest bound be log base 3 of 2? Or
Because
log base 3 of 2. Even if
because our d is greater than log base b of a,
Oh, sorry.
and master theorem tells us that it's n to the d.
Yeah, I got mixed up. Never mind.
No, yeah, that's why I copied and pasted it all the way down, is because I would always get mixed up on it. Okay. So back to this one. For number 7, I can't come up with any counterexamples right away, and it intuitively makes sense that the DFS will only call explore once per connected component. Question?
Doesn't it call explore on every node, so it would be 3 times in that connected component?
That's what I was wondering. So also, if that was all of those 4 nodes were connected,
Mm-hmm.
so if there were 4 edges there, then how would that algorithm work? Doesn't it call explore once it reaches somewhere?
Doesn't the explore algorithm mark a node is visited and then it won't call explore as it's already been visited?
Yeah.
Yeah.
Mhm.
Right?
Oh.
I think that's how it works.
Mhm.
Yeah, that's
Yeah.
what
So then how's it get from, like, say it starts in that top corner, okay.
If you're calling explore on everything in the loop, but it first checks if it's been visited before it explores all its filters, before it does the recursion.
Yeah. So,
So it'll mark all of its children's children visited.
oh, wait. Okay. I figured out how to answer this as well. So explore is recursive, so explore calls explore, but we are specifically asking when DFS calls explore.
Okay.
okay. Yeah.
So DFS is only going to call explore once, and then explore will do whatever it does. Does that make sense? I still saw a couple more hands if people have any more comments. Okay, so I'm going to mark this one as true. I have the solutions open somewhere else so I can double check. If G is directed, DFS will always call explore once per strongly connected component.
True for the same reasons?
Yeah? For the same reasons?
Well, because in an undirected graph, a connected component is a strongly connected component, right? Like that's
True.
what we talked about earlier. So in a directed graph, the same logic applies, right?
So let's say we wanted to call explore from this node in a DAG, right? So the DFS is going to call explore once. All right, now it's going to explore to this one, and then explore is going to call explore, and it's going to reach this one, right? Now, how many times has DFS called explore? Just once. How many strongly connected components are there? There are 3.
So false.
So this one's going to be false. Because each node, if it's not part of a cycle, is its own strongly connected component. This is coming back again.
Would it also be false, like, what if you started at the last node?
Well, if you started at the last node, and then did the middle node, and then did the top node, that would be 3 calls for 3 strongly connected components. So it's specifically where you would start from the source of a chain or a DAG or something like that, where it would be false. Okay. C, if G is undirected, DFS will run in time linearly proportional to the size of G's representation. What does that mean?
It has to do with something with the space complexity being proportional to like the runtime, or like what you said of the matrix.
Mm-hmm. So like in the instance of an adjacency list, what is the quote-unquote size of its representation?
V plus E.
V plus E, right? Because you have a list of V vertices, and each vertex leads to a list of edges that that vertex can reach. Every edge is represented only once. Every vertex is represented only once. So the size of its representation is V plus E. All right. And this is true in both directed and undirected graphs. I mean, technically, okay, edges are represented twice, but then it would be v plus 2e, which is still O of v plus e. All right, and then in D, we consider the directed case, so I'm just going to consider both of these together. In a directed graph, it's also v plus e for an adjacency list. In an adjacency matrix, it's going to be v squared, right? Do we remember the complexities for DFS in adjacency lists and adjacency matrices?
Isn't it v plus e and v squared?
It is.
Okay.
So without having to prove anything and just looking at like how they are represented in the complexity that it is, it certainly seems that it's going to be proportional to the size of the representation in both of these. Does that make sense to everybody? I'm hearing silence. My assumption is that silence means yes, but I'm not sure. Okay. So you are going to see probably a true-false section on the quiz. I wish I could tell you like how to study for it, but the only way I would know how to study for it is to just like know the material, like understand the concepts. I'm not sure you can write a true-false list on your note sheet.
Just list all of the facts.
This just makes it more important for you to actually make the note sheet, remember? Because every time you make a note sheet, regardless of whether you're looking at it, you're studying, right? You're studying and understanding. So that's the best advice I can give, is make a note sheet, and then hopefully you will have the forethought to understand the trues and falses. Okay, question 9. When we have studied algorithms for sorting integers, we've assumed that integers can be compared and copied in constant time. This is a valid assumption for fixed length machine integers, but not for arbitrary length integers. The cost of comparing and copying arbitrary length integers is linearly proportional to their length. All right. So give an upper bound on the worst case running time of merge sort when it is used to sort an array of n arbitrary length integers, each with k bits. Your answer should be in terms of n and k. Oh man.
Boy.
So I don't want the answer here. So I'm just going to start with, at least what we know, right? So we know that the number of comparisons that merge sort is going to do, and if you did last week's homework, you should be deeply familiar with the number of comparisons that merge sort does. We know it's going to be n log n something or other, right?
Yeah.
It's going to have n log n comparisons in it. So now the question is, what is the complexity of every comparison?
K?
K, and where do you get that?
Well, it says the cost of comparing, copying arbitrary length numbers is linear as proportional to their length.
Oof, that's exactly it.
If they're K long, then that means the comparison takes K.
Exactly. So we're going to do n log n comparisons, or order n log n comparisons, and every comparison is going to cost k, however big k is. So we're going to just add a k in front of here, right? And that is going to be how many, or the complexity of how many comparisons that we do. So okay, it says given upper bound. I was trying to figure out where it said bound. So we can give an upper bound using big O. And so the answer to this one would be big O of k times n log n. Question?
Technically, since it just says give an upper bound, not the tightest upper bound, can you just do n to the n times k to the k or something like that?
Can you? Yes. How will we grade you? That's up to us. So sure, if you want to play like that, be my guest. How about I just manually specify we're looking for tight upper bounds here? Okay. Now, give an upper bound on the worst case running time of merge sort when it is used to sort an array of n arbitrary length integers whose values range between 0 and m. Your answer should be in terms of n and m. So m is some big number. This one's a fun one because it's different from the last one. The last one told us how many bits each number had. This one doesn't. You seem to have input.
So the worst case is that they're all m, right?
Mm-hmm.
So then it's just
Or around the size of m. Right?
Well, no, because if it says the values range from 0 to m, we're looking for the worst case running time. Then that means
the worst case ones will.
The worst case ones are all the longest possible integers, which for us is m.
M or stuff of the same length as m. Right?
Oh, I thought that was m bits.
No, this is m size.
Ah, rude.
Like m magnitude. There we go. M for magnitude. So how many bits does a number m have?
2 to the n? Log base 2 of m?
Log base 2 of m. We got there. All right.
I'm doing this backwards.
We don't use log bases here because we always assume to. So it has log of m bits. Well, hold up. Suddenly this is looking really similar to the last one, right? It's just instead of a k, we have a log n. Well, why don't we try that? We have n log n comparisons. We have n log n comparisons in the worst case as well, because again, from the assignment last week, we know the worst case of merge sort is still n log n. And in the worst case per comparison, the worst case of the complexity for that comparison is going to be log of m. That's an m in there. Hold up. Hold up. Oh, please erase. I know you can do it. That's not going to do it. Oh, well.
We believe you.
Oh, I'd erased it. Okay. You understand it, though. It's log of big M times n log n. Or some, multiplied variant of that. I can't say what order everything is going to be in. Does OneNote just crash? Oh, man.
Yeah. It's a Windows product. Of course it just crashes.
I will not take sides.
Windows is crashing. The only correct side is temporals.
All right. Hey, look, we're back.
Isn't that the
And it still has all my notes. Okay, does anybody have any other questions about number 9? I see a hand back there.
So this is actually referring to.
Excuse us real quick. Your question.
This is actually referring to DFS.
Okay.
Does the complexity for DFS change at all if it's a directed or underdirected graph? Or does it really change, except for its application to strongly connected components if it's a directed or underdirected graph?
So, the short answer is no. And the reason for that is when it's calling explore on each node, the node is going to look for edges that come out of it, and it's going to check preemptively if it's visited that node before, right? So in an undirected graph, right, when it got to a node, if it checks along an edge and sees something that it's already visited, even if it just came from that direction, it's not going to bother exploring again from there, right? So the complexity isn't going to change, even though you have technically twice as many edges you can look at because they're undirected. It's still going to be a factor of e. Does that make sense?
Yeah, I guess I'm just figuring out where, if there really is any difference with DFS directed or undirected, except for we see that the application for using DFS for strongly connected components is different, but are there any other differences? Does that make sense?
I can't really think of any other differences. Because, the edges are the same. It's just they go both directions. So, the way you would do the method is still the same, right? Just check everything that you can reach from one node and pick one of those paths. So, that's the best I can come up with. All right. So, We've gotten down to question 10. There's only 14 questions, although I only have 10 minutes. So then, before I just dive into some more yes/nos, has anybody had time to look at the midterm exam review paper? Do you have burning questions that you'd like for me to get to before the end of class? Okay. All right then. Below are 4 statements about the type of blended algorithms that we have studied. Classify each as true or false. Oh yeah, this is a fun one. For sufficiently large problem sizes, a blended algorithm is faster than both of the algorithms from which it is formed. Yes or no?
No.
No?
It's too general of a statement to be true.
It's too general of a statement? Well, I mean, that's not exactly a proof.
No, but it served me while in the past.
So I believe the answer that this one requested was yes. I can double check real quick if it doesn't crash. Oh man, solutions. You're not supposed to see this file.
Everyone quick, take pictures.
So yes, it says yes.
Okay.
So I guess the assumption here is that the blended algorithm has a better complexity than the, well, not the blended algorithm, but the, like the two, like one of the algorithms has a better complexity than the other. I think that's the assumption here. And so with that assumption, it will always be faster than the algorithms for which it was made with sufficiently large
I also
sizes.
forgot to take into account that it's only talking about the blended algorithms we've talked about and not just blending any 2 algorithms for any problem. Because I feel like if you were being hostile, you could come up with a blended algorithm that's worse.
All right, so you've already seen the answers, but the next one, a blended algorithm is asymptotically faster than both of the algorithms from which it is formed. True or false? False. Why must it be false?
Because it's still the same algorithm, it's just that it has a lower bound for what the best is to be.
Exactly. It's still using the same algorithm, right? You can't magically just get a big O performance just by like combining the same 2 algorithms together. At every step, you're still going to be in one of those algorithms. So no, it is not asymptotically faster than both of them. It must be asymptotically the same of at least one of them. At least one of the algorithms from which a blended algorithm is formed must be a divide and conquer algorithm. Yes or no? Why do we think yes?
Because why would you, like, dividing and conquering is the reason you use a blended algorithm. You divide it until it's small enough to use, but not necessarily divide and conquer algorithm. And that might be faster at that level than versus back up.
That is the best explanation I have heard for this. The divide and conquer algorithm shrinks the problem, right? So like, why on earth would you make a blended algorithm if you weren't actually like changing the size of the problem ever? Like, it wouldn't make any sense. So like, you wouldn't even be able to blend it. You would just randomly switch to another algorithm. So yes, one of them has to be divide and conquer.
I'm bored of merge, so we're going to do quick sort now.
Both of the algorithms from which a blended algorithm is formed must be divide and conquer algorithms.
No.
No, because I don't think any of the ones we've looked at so far have been divide and conquer algorithms. Okay. So class gets out at 12:05, right? 12:05. Okay. Let's see. I'm just going to try and do 11 real fast, and then we can get out. So for 11, suppose you want to prove that 3n squared plus 2n is O of n squared using the formal proof technique we discussed in class. If you use n not equal to 2, what is the smallest possible value for c that you could use? Does anybody remember the process for solving these?
Like 0 is less than or equal to 3n squared plus 2n is less than or equal to 2 is less than or equal to cn squared.
To cn squared. Well, cn squared evaluated at n over 2 or greater. All right, so in order to solve these, the best step I always come up with is to just plug in n equal 2 into this equation and see what it gives me. So in this case, when n equals 2, we end up with 3 times 4 plus 4, which equals 16, right? And so if we plug in 2 to just cn squared, well, we get c times 4.
So C is 4.
So c has to be at least 4. So that works for me. Does everybody like understand that process or remember it from the homeworks?
No.
It's worth looking up if you don't. Suppose you wanted to prove that 4 over n is O of 1 using the same formal proof technique. If you have c equal to 2, what is the smallest value for n naught that you can use?
This is 0 is less than or equal to 4 over n is less than or equal to 2.
Is less than or equal to 2 times 1, right? So now we need to find some n naught that we can plug in to make this true. So 2 seems to work, right? We could just plug in n naught equal 2, and we would end up with 4 over 2 is less than or equal to 2 times 1, which is true. We'll put a little check. So n naught equals 2. All right. So that's as far as we are going to make it today. Unfortunately, we didn't get to number 12, but that's something worth studying on your own time. But other than that, I think we'll end class a little bit early today. Thank you all for coming to the midterm. Good luck next week. Huh? The lecture will be posted.